Okay, so the question 2, so this one also from past year final exam question. So here you are given a vector function. Also, just coincident we have only ing, so not all the time you will get ing. NC is a positively oriented, which is becomes the boundary of the portion of the hemisphere given by this equation above the plane z equal to 1. So using the Stokes theorem, you have to evaluate the line integral. Okay, so now just look at what is the information that we have. So we are given a vector field minus y cubed plus tangent x and x cubed plus ey. So C is becomes the boundary of the surface which is part of the hemisphere given by this equation. So we know that we have a sphere with radius 2, but since z is always positive, so we have a hemisphere like this, and C is a portion of the hemisphere above the z equal to 1. So it is not at z equal to 0, but it is at z equal to 1, this the blue one. So you have this particular, so this is your C, the blue one, z, where it is lying on z equal to 1. So the question here, they asking for evaluate the, so they ask for evaluate the line integral of the f dot dr where your curve is a circle. But what is the size of the circle? So in this case, we don't bother about the C, but we want to compute the surface integral. So because the question here asking for using Stokes theorem. So using Stokes theorem, the line integral here can be determined by the surface integral of the curl f dot n ds over the surface sigma. So in this case, your surface is which one will be your surface? So your surface here is only this one, and this is your boundary. Okay, so this one you can erase that. So you can erase the other part. So this is not. So this is not your region anymore. Okay, so that is your surface. So where is your surface sigma? This one. Where? What is the boundary of the surface? This one. But we don't bother about this circle thing here, but we were bordering on the surface because we work on surface integral. So now we want to obtain the surface function. So we want to know what is the surface function given. It is this one. Okay. In this case, okay, so your surface here is given by the hemisphere, right? This one, which is z equal to square root of 4 minus x squared minus y squared. So then remember I told you, so what is the kind of function that you have here? So you have z is the function of x, y, and then from here you can evaluate the now the idea is from here, this one is your sigma. This is confusing. So this is your surface sigma, right? Surface sigma. So now you want to find out your n, where n is always point upward to the surface. So that is the meaning of, look at this one, positively oriented. C is positively oriented, which means that your n should be point outward to the surface. Okay, follow that direction. Okay, where in this case, what is the component that you have to focus on? since you are choosing z is the function of xy, so now you have z, so meaning that you only focus on the component, the vector component of only k component, because we have z there. So we want to have k positive or negative. So this is your surface in that your end is in this direction, your positive end is in this direction, so that is point to the k positive. So we want the k should be positive. So now we want to obtain the end. How can you obtain the end? We have to evaluate the gradient phi. But before that, you have to have the phi first. So z minus 4 minus x squared minus y squared. Okay, and then we obtain the gradient phi, where you have phi x, you have phi y, you have phi z. So differentiate. Okay, phi x. So you have negative 1 over 2, 4 minus x squared minus y squared, negative 1 over 2 minus 2x. Okay, so negative cancel. So you have x over square root of 4 minus x squared minus y squared. And then phi y, also the same, minus 1 over 2, 4 minus x squared minus y squared minus half minus 2y. So when you simplify, you will get y over square root of 4 minus x squared minus y squared. And phi z is 1. Okay, so then when you substitute x over square root of 4 minus x squared minus y squared, y over square root of 4 minus x squared minus y squared and 1. Okay, some of you were asking me whether can we, instead of have z equal to square root, can we simplify z to be z squared equal to 4 minus x squared minus y squared, and then we have z squared minus z squared minus 4 minus x squared minus y squared. Is that possible? No, it cannot be like that. Because why? Because we want to make sure there is the component that we are looking for always equal to 1, the unit component. You must have the component in terms of unit which is equal to 1. So to make sure that we only have 1, so you have to make sure your function here is only a single x, a single y, or a single z. You cannot rearrange that, okay? Because you want to make sure that, for example here, you have z equal to, right? So we want to make sure that the k component, which is part of z, always equal to 1, whether negative 1 or positive 1, as long as the answer is 1. But the rest will can be any values. But this one, because we only focus on k component, so on the k component here, the answer must be always positive 1 or negative 1. Okay? Okay, so when we back to our calculation, finding the n. Okay, so now we said that we want the component k always positive. So now when you check your gradient phi, what the k component you have positive 1. You have positive 1. So since it is already positive, we don't need to modify. So we are looking for positive, right? So to get n, positive n, so the k should be positive. So we got that already. So we don't need to multiply all this with the negative 1. So then we can say this will be our n. Okay. So now remember for surface integral here, instead of we work on the small n, we are working on capital N. Okay, curl F dot capital N dA. Now this one over the region R. So now we already obtained the N. So that is our N. And then we want to compute the gradient F. Sorry, the curl F. So the curl F here is you have only I and J, right? So del X, del Y. So then we put the vector function. So the vector function here is quite long. We have minus y cubed plus tangent x. Tangent x, and then J you have x cubed plus ey. Okay, so we only have I cross J will give you k, so the rest 0. Okay, so we differentiate del x of x cubed plus ey minus del y of minus y cubed plus tangent x. So we have 0, 0, we have 3x squared, and this one negative, negative 3y squared. So we got 0, 0, 3x squared plus 3y squared. So that is our curl F. So then you need to find the dot product between the curl F and the N. Okay, so now you need to multiply this one and this one. Okay, so when you multiply that thing, the components, so x for x, y and y, z and z. So x multiplied by 0, you got 0, plus y component here multiplied by 0, you got 0, plus, and this one 1 multiplied by all those things. So 3x squared plus y squared. So that is your result here. So you already have you obtain the double integral of 3x squared plus y squared dA over the region R. Okay, so now it reduced to double integral. So what is your now in order to determine your dA, then you have to check your function just now here. You have to check here, you have z is the function of xy, so now you know your region is lying on xy plane. So what can you see on the xy plane? So you need the circle here, the size of circle. Even though I mentioned earlier, we don't bother about the size of circle because now you have to integrate, then you have to know the region. So your region is the circle, this circle, this one. So this will become your region down here. Okay, so now your region is circle. So what is the size of the circle on y-axis plane? So we have to find it. Okay, so it to get the circle, it is actually the intersection between the hemisphere and z equal to 1. So then you have to compute that. So you have 1 equal to the square root of 4 minus x squared minus y squared. So you have 1 equal to 4 minus x squared minus y squared. So x squared plus y squared is 3. So you have circle with square root 3, center at the origin. Okay, so here, since you have a circular region, then you have to use polar, is more easier. So you have this one r squared, and then r d theta. Your theta, you have a complete circle 0 to 2 pi, and your r 0 to square root 3. Okay, just for your own exercise, so I don't want to compute this for you, so please complete yourself, and I just give you the final solution. Okay, so hopefully you understand the story about this question. So the question here asking for finding the line integral using Stokes theorem. So since they ask you to use the Stokes theorem, meaning that in your calculation, you have to show me your calculation on the surface integral. So now the time for us to determine the capital N, because we know that we don't use the small n, but we use the capital N here, the big N. So how can we get N? To get N, you have to refer to your information and the given information about the surface. So the surface here is part of the hemisphere, where the equation is this one. And then from your equation of the sigma, you have to determine what kind of function that you have, because this one is very important to determine what is the component, the vector component that you have to focus. Whether you have to focus on component only, the component I, or the component j, or the component k on your normal vector. Okay, so since now you choose z is a function of, so you have to focus on component k only. And this one is also important to determine, to guide you, what is the region, what is your region when you have the double integral here. Okay, so then about the component, vector component, the component of the vector I, j, or k that you have to focus, and you have to refer back to your sketching of this surface and find out, determine the direction of n, where n is always point outward to the surface. So it looks like n pointing this direction, follow the z component, positive. Okay, because we just now focus on the component k of z. So from this arrow telling you that the direction follows the positive k or positive z. So in this case, we set up our n to get positive n, your k must be positive. Okay, so now looking your z here function, then it's time for us to determine the n. To determine the n, you have to determine the phi. So the phi is the function of the surface, which is equal to 0, meaning that you have to bring whether the right to the left or the left to the right. So normally I'll just bring the right to the left, so I got this, and the answer here always equal to 0. So this is our phi, and then you compute for the grad phi, differentiate that with respect to x, y, and z, and we obtain this. And you have to make sure that since you choose a z, so for z component or k component, the answer will be only 1, whether positive 1 or negative 1. Okay, but it is always positive 1. But to get n, to determine n, it depends on your sketching here, whether your component k here positive or negative. Right? So in this case, because we want k positive, and you can see here it is already positive, so we accept all this is n. Okay, so now we manage to get the n. Then we compute the curl f. So in this case, because we only have a component I and j, so I just have this one I and j. So I cross j will give you k, and the rest is 0 automatically. Okay, or if you don't really are confident, so you can just put k component, but k component they are all 0, and the final solution will be the same. Okay, so that is your curl f, and then curl f dot with the n, where you have to differentiate, you have to multiply each component of them, and we got only 3x squared plus x squared, and we substitute here. And then after that, to determine, so now this one reduced to a regular double integral that you have learned before this. And then to determine the order of integration, so find out where is your region. So this will tell you where is your region is. So your region is lying on xy plane. So what can you see on the xy plane from your sketching here? So you can see a circle. Then you have to find out the circle because you want to determine the radius of the circle and also the angle. And then we obtain the value. Alright, so that is the example 2.